Hello again. So today we are jumping back into talking about derivatives. Hopefully, after the last lecture, today will be a little bit easier. I know the last one was almost an hour long. Hopefully, this one won't be that long. This one should be a tiny bit shorter, and honestly, the next lecture should also be a little bit shorter. So, following about an hour-long lecture, we should have two slightly shorter lectures. We are skipping section 3.4, and we're going to go straight to 3.5. So this is where we start talking about derivatives of trig functions, and it does become a little bit more important that we do recall quite a few facts from trigonometry. All right, so let's take a look. So first of all, we have the two most basic trig functions you could have. We have sine and cosine, and these are super important that you just kind of memorize what they are. For the most part, you're probably going to just want to memorize what all of the derivatives of the trig functions are because once you're asked to actually compute them, it'll be a lot easier if you just have them committed to memory. The actual derivatives of these functions you can find if you want to use the limit definition of the derivative. It's just a little bit longer. So I'm okay saying if you want to take these for granted, that's all right. So the derivative of sine is positive cosine, and the derivative of cosine is negative sine. It's very important that we make sure we get our signs, and this is where I now need to specify our SIGN signs, our plus minus signs correct. So cosine's derivative will always be a negative sign, and sine's derivative will always be a positive cosine. All right, and this is a little recollection of the addition rule within a sine function. So this is just a little bit of a note for two important limits that we may see. I believe that we've already seen this one a couple of times. This one, I don't think that we've seen yet. So the addition rule within sine says that the sine of x plus h is the sine of x cosine of h plus cosine of x sine of h. Um, and when you're looking to take the limit as h goes to 0 of the sine of h over h, we get that it's 1. And if you're looking at cosine, we get that it's 0. So these are just two kind of important rules that it's typically just good to know. All right, let's jump right into it. So this is where we have to really remember all of the rules that we talked about in the last lecture because everything is going to start to compound from here on out. So we're going to be expected to know everything that we've done this far. Calculus is a topic that builds on day one, and on day one, you're still using the things on day, well, whatever the last day is, as opposed to something like pre-calc, where maybe day three has nothing to do with day like 57, right? So calculus is all very, very much connected. So I may have mentioned when we were looking at something that was a product that it was a little bit difficult given the knowledge that we had to construct a product rule that we couldn't just use a typical distribution and then the power rule on. And I said that later on, which is now, we will have an opportunity to look at some functions that we absolutely cannot use anything other than the power rule for. This is an example. So we have a function f of x, which is 5x cubed times sine x. So this is two different types of functions. This is a product between a regular old x function and a sine function. So this does need to use the product rule. There's no fun way we could distribute it. There's no way around it. We just have to use this rule. So we want to say, here's our first function, here's our second function. Since we've called this f of x, we would probably want to call these something other than f and g. You can call it whatever you want. If you want to go g and h, we can. I just suggest not using f because then it gets a little bit confusing. So maybe we can say the first one is g and the second one is h, and we can recall what the product rule means. So if f equals g times h, then f prime, if you remember my little trick, it was first times the derivative of the second. So that was gh prime plus second, which is h derivative of the first, which is g prime. So this is the product rule. So let's go ahead and write it out. So g of x is 5x cubed, and h of x is sine of x. And I do typically like to put parentheses around the x so that we're not mistakenly combining the x with whatever's next to it if there's anything next to it. Right here it's clear because it's just a period, but if there's anything next to it, sometimes it's a little bit harder. All right, now let's go ahead and take the derivative. So that implies the derivative of g is, this is our basic power rule, multiply that 3 by the 5, gives us 15x to the subtract 1 from the exponent, 2. And now we can take the derivative of h. h prime of x is, and this is where we remember the derivative of sine is a positive cosine of x. Now we can just go ahead and plug right back into our power rule. F prime of x equals g, which is 5x cubed times h prime, which is cosine of x, plus h, which is sine of x. And this is why I want to put the parentheses, because next to it, we're also going to have some sort of a function, times g prime, which is 15x squared. And like I've said, kind of throughout my videos, this is an appropriate answer. You don't have to go ahead and simplify. In fact, there's no way of combining this other than maybe writing this out front. This is the simplest form that we can get, and this is the derivative of this function using the product rule. All right, let's try another one now. This is a good refresher of the quotient rule. So again, right now, the only tool that we have in our toolbox to actually compute this derivative is the quotient rule. Actually, that's technically not true. I think we can use power rule in this because the variable x is in the denominator, but we're going to use quotient rule. So a reminder, if g is, we'll call it f over h now, then g prime equals, so this is why I use my little tricks, because sometimes we call our functions different things, and if you rely on just f over g, but your function's g, it just gets a little bit confusing. So using my little tricks, it kind of takes the notation out of it. So if you remember, it's low d high, so the denominator, which we call h, derivative of the high function, which is f prime, minus high d low, that's f h prime, over low squared, that's h squared. So no matter what you're given, if you call it this, you can easily come up with what the quotient rule will be using the little slogan here. All right, so let's call f our numerator. So that's cosine of x, and we'll call h our denominator, which is 4x squared, and we'll take the derivatives. So f prime of x is, well, the derivative of cosine is a negative sine of x, and the derivative of h is just 8x using our regular old power rule. Now we can just go ahead and plug back in. So g prime of x is h, which is 4x squared, times f prime, which is negative sine of x. And it is very important that we put parentheses, because if we didn't, this would read as 4x squared minus sine x, which is incorrect. This is 4x squared times negative sine x. So you could theoretically bring the negative in front of this 4 if you'd like. So this is h times f prime minus f, which is cosine of x, times h prime, which is 8x, all over h squared, which is our denominator, 4x squared, squared. So you can leave it like this. I do want to note a lot of times some simple mistakes that we see, like I said, this right here. So if you tried simplifying just a tiny bit, you can rewrite this as negative 4x squared sine of x minus 8x cosine of x over. Another big mistake sometimes we see is when you square this term down here. Sometimes students will only square one of them. I think we just miss it. So when you're squaring a quantity, make sure if it's just multiplication or division within it, you're squaring each thing. And if it's like addition or subtraction, you're foiling it. So here, 4 squared would be 16, and x squared squared, you use the power to a power rule, which means you just multiply. So this is x to the 4. And so this would also be an appropriate answer for our derivative. All right, and here's another application. So we are once again given a position function, which we called s of t, and we're looking for velocity. And we remember that velocity is s prime of t. So it's the derivative of our position function. So it says a particle moves along a coordinated axis in such a way that its position at a time t is given by s of t equals 2 sine of t minus t in this interval. At what time is the particle at rest? So the key here is we're saying the particle is at rest. At rest implies some sort of a speed. So that's not necessarily the position of a function, because at rest doesn't tell us anything about where it may be, but it tells us something about the velocity of the function. And what it tells us is that the velocity is 0, right? If you're driving a car, your car's at rest when it's going 0 miles per hour. So what we're looking for is we're looking for when the velocity is 0, which is the same thing as the first derivative at 0. So the very first thing we have to do is obviously find the derivative. So s prime of t is also the velocity function, so we may call it either one. And all we have to do is take the derivative. So this is 2 sine of t. Well, sine of t has its derivative, which is just cosine. And the 2 out front is just that constant multiple rule that says we can leave it alone. So the derivative of 2 sine of t is just 2 cosine of t. And then minus t, when you take the derivative of just a regular old variable, the derivative is just the number out front. And so this is a -1. And what we need to know is at what times are the particle, what is this going to be at rest, right? So we're looking for when this thing here is going to be equal to 0. So I apologize. It's actually not going to be v of 0. It's going to be when it's equal to 0, when your velocity is 0. I think that would make more sense as well. So when is your velocity 0? Not when your time is 0. Though theoretically, when your time is 0, you should also be at velocity 0, but we don't necessarily know what this particle looks like because it's not a car. It's some weird particle that's just moving in a way that we don't know. So we're looking for when this thing is equal to 0. So 2 cosine of t minus 1 equals 0. And this requires us to remember how to solve for trig functions. So we'll solve it like a regular function, add the 1. So we get 2 cosine of t equals 1. And then we'll get cosine of t equals 1/2. Now, this is where we have to remember how to solve something like this. So what it means to have the cosine equal to 1/2 is that we actually have 2 answers. Because this is a little refresher from pre-calc, you have your 4 quadrants. Cosine is actually positive in 2 of them. Cosine is positive here, and cosine is positive down here. And we have a little slogan. I'll write this. Sometimes we like to refer to this as all students take calculus. And that's STC. And what that stands for is which trig function is positive in which quadrant. So all positive in the first quadrant. This is the second quadrant. Sine is positive. This is the third quadrant. Tangent is positive. And this is the fourth quadrant where cosine is positive. So we're looking for 2 values for t between 0 and 2 pi, which is 1 complete circle, where cosine is positive. So that immediately tells us that we are in the first quadrant and also the fourth quadrant. This also requires us to know our special angles. So if you feel a little bit rusty about your special angles, I definitely suggest taking a look at the unit circle, giving yourself a little refresher. If you need help, definitely talk to me. I have plenty of resources. So here is the refresher on the first quadrant. So we have 3 special angles. And again, we work in radians in this class. If you know them in degrees, feel free to convert. So this is pi over 6, this is pi over 4, and this is pi over 3. And this does correspond to 30, 45, and 60 if you do want to think about it in terms of degrees. And we have coordinates that go along with each one of these points because this is on the unit circle, right? So I have a little trick like I do with most things. I'm going to set up my coordinates. First of all, this is my XY coordinate. This is your trick to remembering the first quadrant, which will translate into every single quadrant. It's just kind of a reflection, positive or negative, of your coordinates. So here's the trick to remember your first quadrant coordinates. So everything has a square root in the numerator and it's over 2 in our denominator. So we're going to go ahead and write that in for everything. Square root over 2, square root over 2, square root over 2. And now we have to figure out what numbers go into those roots. And we have a cool little trick. So we're going to start in the top left. We are going to go down and count up from 1. So we're going to go 1, 2, 3. Well, we stopped here, so we're going to start back up here, count down from 3. 3, 2, if you can read that, sorry, 2, 1. I'll fix that. So those are the special angles in our first quadrant. And we remember that x is cosine and y is sine of some angle value t. And so when we're looking for that angle value t, what we're looking for here is when our x value is 1/2. And we know that the square root of 1 is just 1. And so when we're looking for an x value of 1/2, well, this is an x value of 1/2. So we know that t is pi over 3 because t is an angle measure. But we're also looking for one other spot where we have an angle measure. And we know that cosine is positive in the fourth quadrant. So the way that we're going to find that is using this idea that we are looking in kind of one full circle. If we're looking to find what it is down here, the easiest way to do that is by saying, well, this point here is 0 degrees, but it's also 2 pi degrees, because the idea of a circle is if you go 360 degrees around, you've gotten right back to where you started. 2 pi is 360 degrees. So the easiest way to find the angle measure in this quadrant is by using the idea of a reference angle, which says you take the closest x-axis value and you subtract your reference angle. The reference angle is just whatever angle you are in the first quadrant. So I'll pull it off to the side here. So the closest x-axis value here is going to be 2 pi. And we're going to subtract the first quadrant value, which is pi over 3. And we're going to find the solution. So we can't subtract these because they don't have a common denominator, but we can make them have a common denominator. So we're going to go ahead and change this guy to have a denominator of 3. But what we do to one part of the fraction, we have to do to the other. And so what this actually turns into is 6 pi over 3 minus pi over 3. And this gives us 5 pi over 3. So that's our answer for what t is. So we have t is pi over 3 and also 5 pi over 3. Anytime you're working with trig for sine and cosine, you're going to wind up with two values, whether it's positive or negative. All right, let's find the derivative of tangent. So there will be a rule that you'll just be able to know the derivative of a tangent, but let's actually find a way to solve it. All right, so the first thing is tangent, we have to remember what it means. So tangent is a function, but it's actually a function of functions. So the tangent function is sine of x over cosine of x. And if you think about tangent as this and you're looking to find the derivative of this, so if f of x is tangent, which is sine over cosine, well, sine over cosine is a quotient. So we can actually use the quotient rule on sine over cosine to find the derivative of tangent and prove that it is what the theorem that we'll talk about in a minute tells us it is. So let's go ahead and do that. We'll say, since we have an f function, we'll go g over h. And then the quotient rule tells us that f prime of x is low d high. So that's hg prime minus high d low, gh prime over low squared, h squared. So let's go ahead and set up those. We have g of x equals sine of x, and we have h of x equals cosine of x. So that tells us we can find the derivatives. G prime of x, well, the sine derivative is going to be plain old cosine, which is positive. And when you take the derivative of cosine, that is negative sine of x. Now we can plug in. So we can say, okay, f prime of x is h times g prime. So h is cosine of x times g prime, which is cosine of x, minus g times h prime. So this is sine of x times h prime, which is negative sine of x, all over h squared, which is cosine of x squared. Okay, so normally I would say let's leave it. But because we're looking to find the derivative of the tangent and we're looking to prove that it is what I'm going to say it is, I'm going to simplify this, especially because we see cosine times cosine and sine times sine. So first of all, negative times a negative is positive. So I'm going to go ahead and rewrite this. Cosine times cosine is cosine squared of x. This is mathematical shorthand. Mathematicians are notoriously lazy. So if we write cosine squared of x, that's the same thing as cosine of x squared. So cosine squared of x, again, minus times minus is plus, sine squared of x over, I'm going to rewrite this as, I'll keep it the same, cosine of x squared. All right. Now, We should recognize this as a rule. If not, we should again go back and do a little refresher on trigonometry. So we have a rule. This is called the Pythagorean identity. Pythagorean identity. This comes from the Pythagorean theorem of a squared plus b squared equals c squared, actually. And the Pythagorean identity says cosine squared of x plus sine squared of x equals 1. This is very important, and it's definitely going to come back throughout the course and any other math courses you take. So if we know that we have cosine squared plus sine squared, that's just 1. So this is actually just 1 over cosine of x squared. But this isn't our final answer, because if we consider what 1 over cosine is, we also have other functions. So we have sine, cosine, and tangent, but we also have secant, cosecant, and cotangent. So secant corresponds with cosine, cosecant corresponds with sine, and cotangent corresponds with tangent. And the relationships between them are that cosine is, so secant is going to be 1 over cosine, cosecant is 1 over sine, and cotangent is 1 over tangent. So these are the relationships between kind of the extra trig functions. So if we see 1 over cosine, that's just secant. And if we square it, that is secant squared of x. So the derivative of tangent is secant squared of x. So this is something that you will be able to just use without having to like go through the actual proof every single time. But this is why it is the way it is. And I will show you now this next slide, I believe. Yeah, the rest of the trig functions, so cotangent, secant, cosecant, and their derivatives, I encourage you to try it on your own. Go ahead and confirm that these are the answers. Use your own quotient rule, and it's just really good practice. So the derivative, I do highly suggest memorizing all of them. So the derivative of tangent is secant squared. Cotangent is negative cosecant squared. Secant is secant tangent, and cosecant is negative cosecant cotangent. And again, if you're ever asked to reproduce these, you can just solve them using your knowledge of the relationships between cotangent, secant, and cosecant with sine, cosine, and tangent. All right, now let's do a little bit of an application. So find the equation of a tangent line to the graph of f of x equals cotangent at x equals pi over 4. So now that we have the rules, now that we've already discussed what the derivative of cotangent is, I'm not necessarily going to ask us to go ahead and reproduce the derivative every single time. So from this slide before, we see the derivative of cotangent is negative cosecant squared of x. So we can just use that. So that tells us that f prime of x is negative cosecant squared of x. When we're looking to find the equation of the line, we remember we are looking for y minus y1 equals mx minus x1, where the derivative is in fact your slope. And if we're looking at a specific point, we'll need to find the y value. And then the derivative at that point is the slope. All right, so let's go ahead and find the y value. F at pi over 4. So again, this requires us to know our unit circle. This is cotangent at pi over 4. But what does that mean? Well, cotangent is 1 over tangent, but tangent is sine over cosine. So when you do 1 over a fraction, you actually just flip the fraction. So let's write this. So 1 over tangent of pi over 4, but tangent is 1 over sine of pi over 4 over cosine of pi over 4. But 1 over a fraction, keep, change, flip, is just cosine of pi over 4 over sine of pi over 4. So you can think about tangent as sine over cosine and cotangent as just cosine over sine. So now all we have to do is actually compute these values. So again, we remember we've got these 3 special angles. Pi over 4 is this guy in the middle. And if you did the little trick, you get that this is root 2 over 2, root 2 over 2, where x is cosine and y is sine. So the cosine of pi over 4 is the x value, which is root 2 over 2, divided by the sine, which is root 2 over 2. But when you divide something by itself, you just get 1. So this is the slope. That is your, oh, no, I apologize. That's not your slope. That's actually just your y value. We have to find the slope still. The slope is the derivative. So this is, we'll call this y1. And this is your x. So now we just need m. We already know the derivative function given the slide before. So we can go ahead and plug in pi over 4 into our derivative and find what the slope is. So f prime of pi over 4 equals negative cosecant squared of pi over 4. But I'm going to write this as negative cosecant of pi over 4 squared, because that's what that means. But cosecant is 1 over sine. We don't know how to compute cosecant. We do know how to compute sine. This is negative 1 over sine of pi over 4 squared. Well, the sine of pi over 4 we still have right here. So sine, here's pi over 4. Sine is y. That's root 2 over 2. So we have negative 1 over root 2 over 2 quantity squared. When you square a fraction, you actually just square the numerator and the denominator separately. So we have negative 1 over root 2 squared, cancels out the root and the square. You're just left with 2 over, well, 2 squared is 4. Keep, change, flip. This turns into negative 4 over 2, which is just negative 2. So this here is our m. So now we can just go ahead and plug back in to find the equation of the line. So y minus y1, which we found was 1, equals negative 2, x minus pi over 4. And that is your equation of the line. All right. Now, when it comes to sine and cosine, sometimes we're asked to compute higher order derivatives. And we discussed a couple lectures ago what it meant to be a higher order derivative. And that just means further than the first derivative. So first, second, third, fourth, 58th, 172nd, however many, doesn't matter. That's a higher order derivative. So find the first 4 derivatives of y equals sine of x. So y equals sine of x. Well, first 4, here's the first one, y prime. We know the derivative of sine is cosine of x. All right, so now y double prime is the derivative of y prime. The derivative of cosine is negative sine of x. Not too bad. If we want the third derivative, that's the derivative of the second derivative. Now we have negative sine of x. Well, the derivative of sine is just cosine, but we have a negative there. So we bring the negative down. That's just the negative cosine of x. Not too bad. Now, once we get to the fourth, we typically don't like to use 4 little like tick marks. So we'll just go 4 and then in parentheses, the y in parentheses to the 4. And again, that's not y to the 4th power. That's y to the 4th derivative. So we're taking the 4th derivative. So now we know the derivative of cosine is negative sine. But if we already have a negative times a negative is positive. So this is sine of x. All right, what we notice is these are the same. And in fact, if you were to take the 5th derivative, even though it doesn't necessarily ask us to do that, the derivative of sine is cosine, which you notice is the same as the first derivative. And so in fact, this is going to be something that comes up with sine and cosine. This is like, because it's a periodic function, this is like a cyclical derivative. So every 4 derivatives, it repeats itself. So the first derivative is the same as the 4th derivative. The original function is the same as the 4th derivative, which is the same as the 8th derivative. And you can just continue going up like that. All right, so now let's compute the 74th derivative of sine. Now, you may look at that and be like, whoa, 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 I don't want to write out 74 derivatives of sine. But the cool thing is, using what I mentioned just a second ago, we don't have to write out 74 derivatives of sine. If we remember that sine is a periodic function, and so it's just gonna, the derivatives just cycle about every 4 derivatives, we can actually just use our knowledge of the number 74 to figure out how many times 4 goes around and what derivative would be left off with afterwards. So first, let's look at the number 74. Since we know that sine repeats every four derivatives, I want to find how many fours I can get into 74. Because essentially, if I take the fourth derivative, I get back to the original. If I go four more, I get back to the original. So if I can get rid of that many four derivatives, it's still the same thing as the original. So I can rewrite 74 as 4 times 18. So there's 18 fours in 74, but then there's an extra 2. So 18 times 4 plus 2 is, in fact, 74. But the cool thing is that, again, since we know that every fourth derivative repeats itself, if you do it 18 times, you're still getting back to the original. So this guy right here, when you take that many derivatives, you're just going to get back to sine. And so by rules of exponents, we can actually just take the second derivative of sine. So all we need, so we can say the 74th derivative, and this should have a parenthesis around it, of the sine of x is actually just equal to the second derivative of the sine of x, which is really easy. So we can go ahead and compute that. The first derivative of the sine of x is cosine of x, which tells us that the second derivative of sine of x is the derivative of this guy, which is negative sine of x. Therefore, the 74th derivative, dx to the 74, is also negative sine of x. So this is how we can use the idea of it being cyclical to actually not have to take 74 derivatives. All right, we'll do the same thing with cosine just to show that it actually has the same property. So if y equals cosine of x, then y prime is negative sine of x. Y double prime is negative cosine of x because sine's derivative is cosine, but we have to carry the negative down. The third derivative, well, the derivative of cosine is negative sine, but negative times negative is a positive sine of x. And then the fourth derivative, again, we'll write it like this. Well, the derivative of sine is just cosine of x. And so we see the same exact property here. This is the same value. Repeats every fourth derivative. Oh, alrighty. Well, that is it for today. Hopefully that was a little bit shorter than the last one, and I will see you for the next lecture.